Forecasting is a crucial skill in many, many fields. And it's the topic of our next talk, led by Dennis Bader. Dennis is a senior data scientist and Dart's lead developer at Unit 8. We are curious about your work. Dennis, the stage is yours.
Thanks a lot for this introduction. Welcome to this presentation about harnessing the power of forecasting, including some best practices and use cases. It doesn't work? Maybe go to the next slide. Can you go to the next slide? It doesn't work, sorry. Now it works. Okay. Yeah, I'm not going to introduce myself again. She has already done that for me. Quickly, some words about Unit 8, the company I work for. So we help other companies on their digital journey. And we've been established in 2017, and since then already now more than 100 employees. We are located in 5 different locations across Germany, Switzerland, and Poland. And we've already completed more than 150, 60 projects, all in the data and AI space. And to our services in portfolio, we have consulting, IT solutions, platform integration, operations, and also since a couple of months, the Unit 8 Academy, where we want to teach the best practices across really a lot of different use cases. So for today, I want to quickly give you an introduction to forecasting, show you the best practices that we apply in a forecasting pipeline, and then I want to show you a little bit Darts, which is our open source Python library for time series forecasting and anomaly detection. And in the end, we also look at some of the projects we already completed in that space. Okay, forecasting and anomaly detection. Why do you need this? Here I just give you a non-exhaustive list of different sectors, some of the forecasting use cases that you have, what they are meant for, and then also the business impact that you would have in your company. Here, maybe I just go more into the energy sector. So you could, for example, forecast the demand for an energy good, the price for that good, but you can also perform predictive maintenance. So you want to detect abnormal behavior of some machine, for example, before then actually some serious damage occurs. And yesterday we had a 4-hour workshop around this topic. I already see some familiar faces in here. And all of these tasks you can then use, for example, for production scheduling, better resource allocation, but also then with the predictive maintenance you can monitor the health of your power plant. Then what is the impact for your business? Here in this case, then you could more efficiently manage the power production, reduce costs in the electricity sector. You have to pay a fee if you don't produce as much as you as you promised the last day, for example. But you can also ensure an uninterrupted supply of this energy good, right? So that the electricity grid doesn't collapse. Now, how does forecasting work? The time is a bit limited today, so I cannot tell you about the entire theory, but I really encourage you to read this book, Forecasting Principles and Practices by Robert Hindman and Athanasopoulos. I hope I pronounce his name correctly. They have tons of very practical use cases for forecasting, but also really nicely go into the theory behind it and the fundamentals. And from this book, actually, the first 3 slides I take a bit reference from there. So what can we actually forecast? This slide should show you from very easily predictable to very difficult. And then as a first example, predicting the time of the sunrise today in 1 year, that's very predictable, right? We can basically already know that now by just guessing. But the total electricity demand for tomorrow is already a bit more challenging, but still kind of okay. If you want to predict the electricity demand in 3 days, that's already more challenging because you need to predict further into the future, which makes it more uncertain. And then even the hourly electricity demand in 3 days, more complicated because now you need to predict 24 hours instead of just 1 day. So the number of time steps that you want to make predictions for, of course, also plays a role. Then many people ask this, can you predict the stock prices of a company? You could, in theory, if you knew about all of the factors that contribute to a change in stock prices. But typically, no one really knows all of this. And then that's really the most challenging task, or also human behavior, very unpredictable. What influences then the predictability of a time series? So the most important thing is how similar is the future to the past. The more similar it is, the easier also then to forecast. Also, how well do we know the factors that contribute to this time series? Here, if you look at the violet curve, if you knew that it was just a multiplication of a sine wave and a linear curve, then it would be very easily predictable. Another question, how much data do we have available? Of course, as in any machine learning modeling task or modeling task in general, the more data you have available, the easier it is for the model to learn from this and make better predictions. And then the last one, and this is also crucial, so does the forecast itself affect the evolution of this object that we try to forecast? It should not affect it. So think about if everyone could perfectly predict the stock price for tomorrow, then the stock price would probably not be the same tomorrow. So yeah. Now let's look at the best practices. First of all, of course, you have to define your forecasting task. So first question is, what variable do we actually want to forecast? And then also, how far into the future do we want to forecast? Do I want to make a 1 week prediction, a 1 year prediction, and also the time interval for these time steps that you want to predict? So do I want to predict daily forecasts for 1 week, or do I want to have monthly forecasts for 1 year? Also, do we want to make point predictions, so you predict single values for each time step, or do you want to make uncertainty interval predictions? Usually the latter is a bit better because you might be more interested, let's say, okay, with a 90% probability, I expect the actual value to be within this interval, rather than saying, I'm 100% sure it's 100.5 exactly at that time tomorrow. And then the next one, what available data do we have, and also what do we want to use for modeling? This is really one of the most important factors how you can further improve your model performance rather than just looking at this time series that you want to forecast only. So external features means other variables that you don't want to forecast, but which could help the model improve the predictability of your time series. So that could be, let's say, you're in retail, you sell a product, and you see at Christmas somehow we sell much more than on other days. So you could have like an encoding for when is Christmas as a external variable that you feed to the model, and then it can better learn on this. And then, of course, which model should we pick for the forecasting task? And here, yeah, it's usually you compare different models with each other and then pick the one that best suits to the task. And this is basically what we then do in this robust forecasting pipeline. So you have two parts. One is the modeling part, where you train your model, you find the best suitable model, and then you move this into the production level, where you run it on a scheduled basis, and maybe even, or the best practice is then to monitor the performance of your model also over time, because maybe at some point you need to retrain it. I'm not going to go into too much detail, but of course it involves the data processing, so data cleaning. Maybe you want to remove some seasonality from your data, the trend from your data, for the model to have an easier job. Then the feature engineering, very important. Like, what features do we actually want to use as model input? Also, what time steps may be compared to the forecasting point in the past and in the future do we want to include as information? But then also these daytime features or calendar information, such as holidays, the day of the week, the hour of the day, and so on. You can, of course, also generate your own features. This also sometimes really help boost the performance. And then for the modeling itself, you would pre-screen like this catalog of models for the one that is suitable for your task. Some models cannot make probabilistic predictions, others can. So just pick the ones that are right for your task. Then you would create your dataset splits to perform maybe hyperparameter tuning. You cross-validate. You can maybe perform feature selection and so on. In the end, then, you want to evaluate your model. And here it's important to not choose only one, but multiple metrics. And they should also then, of course, be relevant for your business use case, right? And the way how you validate a forecasting model is not just predict once a one-day forecast, but you want to see how would my model have performed over some time. And then you want to have a model that has like the same amount of error over each day. So to reduce, like, you don't want your model to be super good in summer but very bad in winter, right? And this is called what we call this backtesting, also residual analysis. So how would this model have performed over time? In the end, you compare all of your models, you pick the best one, and then you move it to the production where you monitor the performance in real time. And for this, we then also have anomaly detection. Like, you can detect whether your model shifts away from the expected performance, and in that case, you could then either trigger a model retraining or you even do it on a scheduled basis. And now, darts. So this is where we come in with darts. We developed this around 5 years, or we started developing it around 5-6 years ago. First just in-house, but then we saw how powerful it was and we decided to open source it. And since then it gained a lot of traction. We are now around, I think, the top 3 biggest forecasting libraries worldwide for Python. So what does it do? We make it very easy to manipulate time series, forecast, and perform anomaly detection. And how? Like, we have a very user-friendly API. If you're familiar with scikit-learn, it works pretty much the same. And with this API, you can try out all these 40+ different models in the same way. And we have classic statistical models to neural networks, all in the same way. We also offer, a bit cut here, but yeah, rich evaluation support, including these metrics, backtesting, and residual analysis that I just mentioned, but also really some cool user guides and examples that you might have it a bit easier to jump into the field of forecasting. So what do we want to do is basically we want to try out these 40 different models in hopefully just a few lines of code and then get some very nice forecasts as shown here, even with an uncertainty interval prediction. And you can do this all with darts here. This is in 7 lines of code. I generated these forecasts that you just saw before. Of course, this is just a little example, but we really offer from the data processing then to the anomaly detection for the model screening, the whole end-to-end solution. And now for the end, I want to show you some projects that we actually completed already. We realized that, like, especially in the energy industry, there is a great demand for forecasting, especially now with the renewable energies coming into the market. You really want to know at each moment in time what is the demand of consumers for that, for electricity, for example. Then also in retail or in general for like supply chain optimization, you want to know the demand for your product so you can properly plan ahead. But also predictive maintenance. We had a major Swiss hydropower producer that had a pumped hydro storage power plant, and they wanted to perform predictive maintenance on this pump turbine, which was really cool because since we developed this for them, they actually caught a very big anomaly where one of the engineers had to clean some valves in this turbine, and he forgot to put it like into the original position, like the valve openings. And our approach then signaled this to the operators, and they could react immediately and close them again. Another one really cool was the furniture sales forecasting use case. We finished this like 1 or 2 months ago. This was a global leading furniture manufacturer that had over 1 million different products on a store level. And they wanted to have like one model or maybe multiple models which could predict the future for the next 2 years of weekly sales for each of these products. And so what we did for them was we developed a forecasting framework with darts to benchmark, tune, and select models, but we also coached them on really like why did we apply all of these steps in this whole modeling pipeline. The resulting model that we picked was a neural network that we trained on 10,000 of these products, and then we used the same pre-trained model to predict the rest at once. So we beat their existing solution, which was very slow. This neural network, you train it for just like half an hour, and then you can produce these forecasts very, very quickly. And the accuracy was also much better than what they had. And now they can more optimally plan the supply, but also use this framework for new forecasting use cases. That was it. Thank you very much for being here. This is my email address if you want to reach out. Otherwise, we're also at the booth later on. And if you have any questions, now I think is the time, right?
Yes, are there any burning questions? We have a hand microphone if you want to ask. Yes, please.
How do you feed in events into the forecasting? You know, those that produce peaks or that lag or something?
Events, you mean like at this point in time something happens or what?
Yeah, you know, just you have a flooding and suddenly, you know, all the predictions for energy go wild, or either drought or something, or there's a power outage on one day or something. How do you factor those things into the forecasting so that you don't, you know, with past events, you don't...
Okay, so if you already, for a power outage, for example, if you already had some power outages in your historic data, then you can label this maybe like 1, it was true was a outage, 0 was no outage. So you can use this as one of these external features, and we call this past covariates in darts. So these are variables which you only know in the past, and you don't want to predict them, but you want to give it to your model so that it learns, okay, these were some anomalous periods where an outage happened, and the model should learn this. And then also for the future you would say just set this variable to 0, like you don't expect a power outage, and then your model would predict as if no outage will happen, for example. Does that answer your question? And otherwise, if it has never happened before, then you maybe have to think about model retraining. Like maybe you need to fine-tune it a bit on the most recent past, where you now have really a very different behavior than what you had before.
Is there another question, or do you want to have lunch? There's another question, sorry.
Short question. You were mentioning these 40 different models. Is there like a pattern that emerges, like which model is like used the most, or which one would you recommend like diving into?
I would always recommend starting with the very simplest models, the naive approaches. Sometimes you really can just repeat what happened in the last 12 months ago to make a prediction for the next month. That is a naive estimation, and usually they're already pretty good. And then you compare all these other models to that. So you take this naive model as a reference, and then you use more sophisticated models. And there, like, I'm really a fan of regression models in the space of forecasting, they're very powerful. Like a linear regression model can not only predict a linear curve, but even sine waves and everything, because it's just a different manipulation of the data which allows this. We explain this in the documentation, it's a bit too much for now, but also the neural networks, like they have such power and they don't need to be trained on millions of different time series. It also doesn't take hours to train them. So for example, for electricity demand forecasts on a 50-minute interval for 2 weeks, there was another project we had. A neural network learned this in 10 minutes and it outperformed all of these statistical classic models from ages ago.
Thank you for your presentation. We close with a big round of applause and a small gift to you.
Thank you.